The knapsack problem is a very typical case of what we call dynamic programming, where we essentially memorize some values, breaking down the problem in smaller parts, and gradually we find the optimal solution of the problem. We can think of the knapsack problem as having a set of items, and each item has a weight and a value. And we have a container that can hold up to a specific total weight. Let's call it maximum capacity. The objective is to find the subset of the items given that can fit in the container without exceeding maximum capacity, but also maximizing the total value. In other words, it's an optimization problem under a specific constraint. One thing we have to notice here is that each item can either be contained or not. We cannot take fractions of it. That's why sometimes this problem is known as knapsack 0-1. So to make things easier to understand, let's assume that we have an array of items, in this case indexed from 1 to 3, 1, 2, and 3, and each of them has a weight and value. In this case, 8 kilogram has a $17 value, 4 kilogram has $12, 3 kilogram has $6. And we have a bag which can hold up to 10 kilograms. In this case, we only have 3 items, so the solution is obvious, meaning if we create all the possible combinations with these 3 items, which is going to be 8 if we include the non-item, we can see the brutal solution, meaning in this table here we can see all the possible combinations. We can have the 3 items, which is 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, and 1, 2, 3. Here we have the cumulative weight for them, and here we have the cumulative value. Immediately we see that items that exist the maximum capacity when added together should be automatically discarded. For example, 1 and 2 is 12 kilograms, 1 and 3 is 11, 1, 2, 3 is 19. They do not fit the bag. From those that they fit the bag, we see that the maximum value, which is 18 in this case, is being found when the cumulative weight is 7. Is the 2 and 3. That when we combine 2 and 3, the total weight is 7, while the value is 18. And this is the maximum we can get. The next one is item 1 alone, which is less than it. And the same applies to the other combinations. The problem with this solution is that it requires us to create all the possible combinations. So assuming that we have n items, the total number of combination is going to be 2 to the nth power. Meaning here we have 3 items, the combinations are 2 to the 3rd power, which is 8. If we had 4, it would have been 16, and so on. So this number grows very fast, the complexity is very high, and we have to find a better algorithm that can serve our purpose, within reasonable time frame. So let's make our example a bit more interesting and assume that we have 5 items, those that we can see here. Each of them has an index 1, 2, 3, 4, and 5, and we are sorting them by weight, meaning smaller weight is before larger weights. And as you can see, to make our life easier when it comes to calculations, we added one dummy item which has weight 0 and value 0, and we're going to see when we're going to implement the algorithm how this makes our calculations simpler. For now, we keep that the items are sorted by weight. And we also are given a knapsack that has a maximum capacity of 10 kilograms. So we have these 5 items that we want to fit in a bag of capacity 10. Let's see. Again, I repeat that we added one item with weight and value equal to 0, which doesn't change our solution at all, but it makes the implementation a bit easier. And we keep the items sorted by value in a decreasing order. So now that we added the 0 weight item, altogether we have 6 items. And if we calculate the weight of 0 as well, we have 11 possible discrete weights, starting from 0 to 10, including 10, there are 11 values. Now, think that for each item, we're going to create 11 different bags, one for each discrete weight. Altogether, we're going to have 66 bags for each possible capacity that they're going to correspond to a specific item. These 66 bags are represented in this picture by the yellow colors, which are elements in a two-dimensional array. It's a two-dimensional array. The rows correspond to the items, which are 6 from 0 to 5, while the columns correspond to discrete weights, which are 11, and they start from 0 to 10. So each cell, each element in this array, in this two-dimensional array, we can think about it like a bag. This is a bag that has some capacity, and we need, to fill each of them with the maximum value that we can get from these items. Thinking of each element of the array as a bag means that we can start filling each element one by one from left to right for each row, and always using either the current item of the row we are or the items above us, never the items that are going to come later as we increase the row. So for example, the element here that we can see from the row arrow, it points to a bag. This bag has capacity 3, because remember, this index is the maximum capacity of the bag, and it has access to 3 items, to item 2, 1, and 0. What we want is that at any point, the value of each element in this array to be the maximum value given the capacity of the bag and the items that have seen before. So Our objective, again, is to fill this 6 by 11 array with the maximum possible value that each bag can hold based in its capacity. Again, each cell in the yellow array we can think about it as a separate bag. If we manage to fulfill all the elements in the array, the one that it is in the end, the last item, which in this case is this green element, is going to hold the maximum value that we can hold in the bag of capacity 10 using this array of items. Now let's start inserting a row at a time. We go row by row. The first one, the index and the value is 0, the weight is 0, so it is obvious that all the bags for row 0, they're gonna have a value, a maximum value of 0. There is nothing else. So we have no items, no value at all. Now moving to the next to the next element is a little bit more interesting. In this case, as we can see here, we have to add the index, the item indexed 1, which has a value 2 and a weight 1. So if we start from the first bag, the first bag has a maximum capacity of 0. Since the weight for this item is 1, this means what? This means that we cannot fit this item in the bag. So we keep the value unchanged, and we say that the value of this bag remains as it was before, becomes 0. Now we move to the next element. The next element lives in a bag that has a maximum capacity of 1. Since the weight is 1, then this can fit in this bag, and this is what we're doing. We're taking this element and we're placing it in the bag with the capacity 1, and we mark it with the number 2, meaning that the maximum value for this bag is 2. This means that having only the first item, the item index 1, the maximum value we can carry for it is 2. And note that when we enter the item 1 to the bag, there is no more remaining capacity. We completely exceeded the capacity, plus the previous value was 0. So we are fine. We are increasing in value, and we are sure that this is the maximum value we can have with this item. Now, obvious for the rest of the array, things work exactly the same. We don't have any other items except the first one, so what we end up is the schema we see in this picture. 0 and everything else is 2. Now adding the third row, which corresponds to index 2, which has a value of 6 and a weight of 3, is a little bit more interesting. The weight of this item is 3, so obviously it does not fit in the first 3 bags, the one which has 0, 1 and 2 capacity. So they're going to remain as they were before. They're going to remain 0, 2 and 2. Now, when we move to the third bag, which has maximum capacity of 3, our item now, it fits to the bag. If we add item index with 2 to the bag, our value is going to become 6, and we have no more capacity. That's the only one we can have there, and the value before was 2. So this means that we should go ahead and place this item to the bag, being sure that the maximum value that we can take from these 3 items, the 0, 2 and 6 value items, is 6. This will never change. This is going to stay the same until we finish our algorithm. Now let's go and add the fourth one. The fourth is even more interesting. As you see, I have it with a question mark, meaning we have seen how we populated the first line, everything 0, the second line, the third. Now our capacity is 4 and our weight is 3. So if we add this element, this item in the bag, the value is going to become 6. But we have 1 kilo left. The question is, how do we fill this kilo? To fill it, we can use the bag that has capacity 1 and has access to all the items we have seen here except the current one. In other words, we have to go back 1 row to row index 1 and find the bag with capacity 1, which in this case is 2. So now if we add 2 to 6 with 6, we get the value 8. Since 8 is larger than 2, which is the value that our bag had before, then it is easy to understand that we have to place the value 8 to the bag with capacity 4. And by doing so, we're getting to this point here, where now we know enough to create a genetic algorithm to add any item to a specific element of the array, except the first one, which is all zeros, and we know how to handle it by default. So if the item weighs more than the maximum capacity of the bag, we don't do nothing. We just leave the bag as it is and we carry on the maximum value. In the opposite case, that the item weighs less, is the item's weight is less or equal to the capacity of the bag, we have 2 choices to pick from. Either the value as it was before is going to be the one we're looking for, or the value of the current item added by the value of the carry on item that we can use the remaining capacity to combine it with it. In pseudocode, what I just said can be expressed by this formula here, where we check if item's weight is more than the capacity, we just carry on. Else, we are finding the remaining capacity, we are adding the value of the bag in the previous row for the remaining capacity to the value of the item, and we populate the element with the maximum of the V1 and the previous value for this row. This is a generic formula that can be applied to any cell in the bags array. Once we understand this, everything else is trivial. So if we follow this formula, we can go ahead and we can fill out the whole table. All these values were added using this formula, and we ended up that the bag with capacity 10 has a maximum potential value of 26 for items that weigh less or equal to 10. We have not finished yet our problem, because although we know the maximum value, we still do not know the items that consist this value. So the way to do this is the following. We always start from the last element in the array, the one that holds the maximum value. If the value in the same bag capacity, the capacity 10, is the same in the previous row as it is here, this means that the item in the last row, in this case, is not included in the optimal solution. Because if it was included, the weight would have been larger. So we mark it with black, which means is not included. Then we move to the next item, the next element going on top, the green 26, which we see that the item above has the value 20, which is less than 26. This means that the item with index 4, which was added in the optimal combination, in this case we mark it with a check mark, as we see here, and then we subtract from the maximum capacity of this bag, which is 10, we subtract the weight of the item that we just included, and this is 5. So then we move to the previous row and we find the bag with capacity 5. In this case, this capacity has the value 14. So the bag here with capacity 5 has the value 14. Its previous value is 8. This means that this item was included in the optimal solution. So we mark it with check and do the same thing. We subtract 5, which is the weight, the maximum capacity of the bag, from 4, and we get 1. And we go again in the previous row at pointer 1, meaning in the bag with capacity 1, and we find the number 2. The previous bag from 2 has the same value. This means that the item indexed 2 is not included in the optimal array, and we mark it as done. And we move 1 row higher. Then we see the number 2. The value is 2. The previous was 0. So this was included. Its weight is 1. The weight of the bag is 1. So we move to the final item, which happens to be the first one, the 0, and we know that we are done. So we conclude that the items that make up the largest value with the constraint of weighting less than 10 consist of item 1, 3, and 4. And a few words about the complexity of the solution. Since we are going through an n by m, where n is the number of items and m is the number of distinct weights, the complexity of the solution is n by m. And the same thing applies for the space complexity, because we have to allocate an n by m array. So although this number, for very small numbers of n and m, it might be larger than the 2 to the n solution, when these numbers grow, the difference is tremendous. It is much, much faster. We're gonna follow with another video with the implementation of this logic using Python. Thank you.